Hello everyone, welcome to the video lecture of this course finite element method. So this is the fourth lecture of the fifth module regarding the isoparametric formulation or isoparametric concept that we are going to discuss. So earlier in this module we have discussed the concept of the isoparametric element, then the natural coordinates and the concept of the shape function and the formula for the shape function in case of the quadrilateral element, then the concept of the isoparametric, subparametric and superparametric elements were discussed. Next, we have also discussed the formula regarding the stress-strain relationship matrix and stiffness matrix, and based on those different formula we have discussed and we have solved different numericals. Now today in this lecture we will solve some more complicated numericals where we will discuss the procedure to solve the isoparametric elements numerical so that we can calculate the Jacobian matrix for such isoparametric elements. Okay, so let us start this lecture. So these are the course objective and course outcomes for this subject, finite element method, where we are having two course objectives and four different course outcomes which are known to us. This is actually the COPO mapping for this subject. Now we will start this lecture, the discussion from this numerical problem. So what this question says that a four-noded rectangular element is shown in figure 1. We need to determine the following, which are a Jacobian matrix, then strain displacement matrix, and number 3 element stresses. Some data are given here, like the Young's modulus E equals to 2 into 10 to the power 5 Newton per millimeter square, then nu equals to 0.25, the U vector or U matrix it is given, then epsilon and eta at local coordinates, these are given as 0, and it is told that we need to assume plane stress condition. So these are the three different things we need to calculate, which are Jacobian matrix, then strain displacement matrix, and the element stress for this given four-noded rectangular element. Now let us start the procedure to find all the three different things. So first we will identify and write what are the things given in this numerical, and from that what are the things we need to find ultimately. So here the coordinates of this element, quadrilateral element, these are given. It is in case of node 1 it is given the coordinate as 0 0, that means x1 is 0, y1 is 0. Then for node 2 the coordinate is given 2 0, that means x2 is 2 and y2 is 0. Then for the node 3 the coordinate is given as 2 1, so that means x3 is 2 and y3 is 1. Next for the coordinate node 4 the coordinate is given 0 1, and that means the value of x4 is 0 and y4 is 1. Now the value of the Young's modulus is given 2 into 10 to the power 5 Newton per meter square, and the value of Poisson's ratio it is given 0.25. And the displacement U, this matrix is given as a column matrix, and the natural coordinates or local coordinates epsilon is given as 0 and eta is given as 0. So these are the things or the values of the parameters which are given in this numerical, and we need to find the Jacobian matrix, then strain displacement matrix and the element stress. So let us start the procedure to solve these three different things. So first we need to calculate the Jacobian matrix for the given quadrilateral element, and the formula for this Jacobian matrix J, this is equals to this 2 by 2 matrix, which is J11, J12, J21, J22. Now we need to calculate all these four different matrix elements. So the formula for J11, this is actually 1/4, then within bracket minus 1 minus eta into x1 plus 1 minus eta into x2 plus 1 plus eta into x3 minus 1 plus eta into x4, which is our equation number 1. Now in this equation, if we put the value of eta as 0 and the values of the x coordinates for the given quadrilateral element, in that case we will get the value of J11 as 1. Simplification is given here. The value of J11, it is equals to 1. Next, the formula for J12, it is given here as equation number 2. Now in this formula, if we put the value of eta and y1, y2, y3 and y4, that means the y coordinates of the four different nodes of the quadrilateral element, in that case we will get the value of J12 as 0. Next, to find the value of J21, we will use the formula which is given here as equation number 3. Now in this equation we need to put the value of epsilon and x1, x2, x3, x4, that means the x coordinates of the nodes of the four different nodes of this quadrilateral element, which are given in this numerical. So that means putting all these known values, we are getting the value of J21 as 0. Next, to calculate the value of J22, we need to use this equation number 4. Now in this equation number 4, we need to put the value of epsilon and the y coordinates for the four different nodes of the given quadrilateral element. If we put all these known values, then finally we are getting the value of J22 as 0.5. Now as we have calculated all the values of the Jacobian matrix, that means we need to only put this value inside that matrix, and that means we are getting the Jacobian matrix as 100.5. So this is the Jacobian matrix here, and the determinant, it is now 0.5. So this is the answer of the first part of this numerical. That means we have calculated the value of the Jacobian matrix, which we are getting as the matrix is 0.5 and the determinant of the matrix, it is 0.5. So the first part of this numerical, it is now completed. Next, we need to calculate the strain displacement matrix for this quadrilateral element. Now the formula for this strain displacement matrix for the given quadrilateral element, it is written here. It is the B matrix, it is 1 by J, determinant of the J, then a 4 by 3 by 4 matrix actually multiplied by 1/4, then it is also multiplied by another matrix, which is a 4 by 8 matrix. So this formula, it is actually very complicated formula to calculate the strain displacement matrix. So we need to practice a lot to remember this formula of the strain displacement matrix for this isoparametric element. Now if we put the values of J11, J12, J21, J22, then J determinant, eta and epsilon values in the strain displacement matrix, so ultimately after several steps and after a matrix multiplication, we are getting the value of the strain displacement matrix B. This is 0.25 multiplied by a 3 by 8 matrix, which is given here as equation number 7. So we need to only remember the formula of this strain displacement matrix, which needs a lot of practice, and if you can remember only this formula, then we can easily calculate the strain displacement matrix value, which we are getting here as equation number 7. Now for the third part of this numerical, we need to calculate the element stress, which is sigma equals to some matrix multiplication, which is D matrix multiplied by B matrix multiplied by U. Now the value of D matrix we have already calculated, which you can see here as equation number 7. The displacement dot U matrix, it is given in the numerical, and that means we need to only find the value of the D matrix. Now this D matrix, for it is actually a stress strain relationship matrix. Now we need to take into assumption the plane stress condition, which is given here in the numerical. Now considering the plane stress condition, the stress strain relationship matrix or the D matrix formula, it is E by 1 minus V square nu square multiplied by a 3 by 3 matrix. Now the value of this Young's modulus and the Poisson's ratio, these are actually given in this numerical. So we need to put the value of this Young's modulus and Poisson ratio in this stress strain relationship matrix. And finally, after several steps, we are getting the value of the stress strain relationship matrix D as equation number 9. Now to calculate the element stress, we need to put all the values of the D matrix, then B matrix and the U matrix on the displacement vector. So some matrix multiplications are needed here, which we can see here. So we need to be very cautious and serious to calculate or to perform this matrix operation. So after these several steps, we are getting the value of this element stress sigma. This is equals to a column matrix of 480, 120 and 280 Newton per meter square. So this is the final value of the element stress. So the final result is written here. That is the first part of the numerical. It is the Jacobian matrix calculation, which we got here as 1000.5, this 2 by 2 matrix. And the value of the strain displacement matrix, that is B, this is given here as 0.25 multiplied by a 3 by 8 matrix. And the third part of this numerical, that is the calculation of the element stress, which is the sigma vector, which is a column matrix of 480, 120 and 280 Newton per meter square. So this is the procedure with the help of which we have calculated these three different parts of this numerical. So we need to remember the formula for the Jacobian matrix, then the formula of the strain displacement matrix, and the formula of this stress strain relationship matrix. So let us move to the next numerical. For the isoparametric quadrilateral element shown in this figure, the Cartesian coordinates of point P are 6, 4. The loads 10 kN and 12 kN are acting in x and y directions on that point P. So we need to evaluate the nodal equivalent forces. So let us write in details what are the things given in this numerical. The Cartesian coordinates of the point P, which is inside this quadrilateral element, it is given 6, 4. So that means x is 6 and y is 4 for the point P. Then the Cartesian coordinates of the 4 different nodes, that is 1, 2, 3 and 4, these 4 different nodes, the Cartesian coordinates are given. So that means from these given points we can write the value of x1, x2, x3, x4 and y1, y2, y3 and y4. The loads acting here are given. Fx is 10 kN and Fy is 12 kN. Now we need to find the nodal equivalent forces for x and y directions. So that means we need to find F1x, F2x, F3x, F4x and F1y, F2y, F3y and F4y. So these are the things that we need to find in this numerical based on the values given here. So first we will start with the formula of the shape functions here. The formula for the 4 different shape functions corresponding to the 4 different nodes of a quadrilateral element in case of any isoparametric element, it is given as n1 equals to 1/4 1 minus epsilon into 1 minus eta. This is our equation number 1. Then n2 it is 1/4 1 plus epsilon into 1 minus eta. This is our equation number 2. Then n3 is 1/4 into 1 plus epsilon into 1 plus eta. This is our equation number 3. And n4 this is equals to 1/4 into 1 minus epsilon into 1 plus eta. This is our equation number 4. So these are the equations for the shape functions that we need to remember. Now the formula of the Cartesian coordinates of the point P, it is xy, it can be represented here x equals to n1 x1 plus n2 x2 plus n3 x3 plus n4 x4 and y equals to n1 y1 plus n2 y2 plus n3 y3 plus n4 y4. So these are our equation number 5 and 6. Now if we substitute the values of x, x1, x2, x3, x4, then n1, n2, n3 and n4, these values in equation number 5, then these are the steps which are given here. So we need to perform these 5 different steps and finally we are getting the equation number 7, that is 9 eta, it is 9 epsilon minus eta minus 3 epsilon eta, this is equals to 5. So this is our equation number 7 that we have got here, and corresponding to the y coordinate we need to substitute the values of y, y1, y2, y3, y4 and n1, n2, n3 and 4 values in equation number 6. So finally after several steps we are getting one more relation in between epsilon and eta which is 4 epsilon plus 6 eta minus 2 epsilon eta, this is equals to 0. Now from this equation number 7 and 8 we need to find the value of eta and epsilon. So how to calculate that one? Here what we have done, we have multiplied equation number 7 by 2 and equation number 8 by minus 3. So that we are getting equation number 9 and 10 here, and from these two different equations we can easily calculate the value of eta in terms of epsilon, which we are getting as equation number 11, which is eta equals to 0.3 epsilon minus 0.5. Now if we put this value of eta in equation number 7, then after several steps we are getting one equation that is 0.9 eta epsilon square minus 10.2 epsilon plus 4.5 equals to 0, which is in the form of ax square plus bx plus c equals to 0. So from this we can use this formula, which is very familiar to us. So finally we are getting the value of epsilon. This is as 0.46. Now if we put this value of epsilon in equation number 11, then we can calculate the value of eta as minus 0.362. So now if we put the value of eta and epsilon in the formula of the shape function, then we can calculate the value of shape function n1. This is 0.18387. Then in case of n2 we are getting its value as 0.49713. Then the value of n3 we are getting as 0.23287. And the value of n4 we are getting as 0.08613. So these are the values of the shape functions that we have calculated here. Next, the formula of the element force vector Fe. This can be mathematically represented as n transpose multiplied by Fx Fy, this column vector, column matrix. This is our equation number 12. So the value of element force vector Fe, this is actually the column matrix of F1x, F2x, F3x, F4x. So this is equals to n1, n2, n3, n4, a column matrix multiplied by Fx. Now the value of these shape functions and the value of Fx, this load, it is known to us now. So we can put the values here and we can calculate the value of F1x, F2x, F3x and F4x. And in this similar manner, we can also calculate the value of F1y, F2y, F3y and F4y, which is actually the formula of the column matrix constituting of the shape functions multiplied by Fy. The value of Fy is given in the numerical, which is actually 12. So if we do this matrix multiplication, then we will get the value of F1y, F2y, F3 and F4y as a column matrix. So that means the result can be written in this manner. The nodal forces for x direction we can write here as a column matrix, and the nodal forces for y directions also we can write here as a column matrix. So this is the procedure to calculate the column matrix in case of a quadrilateral element. We need to use the formula of the shape function, and from that we need to find the value of the nodal forces. Let us discuss the next numerical, where one isoparametric quadrilateral element is given and we need to evaluate the Jacobian matrix for this given isoparametric quadrilateral element. Now, from the given coordinates of the four different nodes of this quadrilateral element, we can write x1 equals to 1, y1 equals to 0. And corresponding to node 2, we can write x2 is 2 and y2 is 0. And corresponding to node 3, we can write x 3 is 2.5 and y3 is 1.5, and corresponding to node 4 we can write x4 is 1.5 and y4 is 1. So in this numerical we need to find the Jacobian matrix. So we will start with the formula of the shape function for the isoparametric quadrilateral element. The formula of the shape function is n1 equals to 1/4 1 minus epsilon into 1 minus eta, then n2 is 1/4 1 plus epsilon into 1 minus eta, then n3 it is 1/4 into 1 plus epsilon 1 plus eta, and n4 is 1/4 1 minus epsilon 1 plus eta. So these are our equation number 1, 2, 3 and 4. And for this quadrilateral element, the Cartesian coordinates formula, these are also known to us, which can be mathematically represented as equation number 5 and 6. So this mathematical representation or the formula of the shape function or the Cartesian coordinates, these are known to us. We have used this to solve some problems that we have discussed earlier. Now if we put the values or substitute n1, n2, n3, n4, then x1, x2, x3, x4 and y1, y2, y3, y4 values in equation number 5 and 6. That means in case of equation number 5, suppose x equals to n1, x1. Now the formula of n1, it is given here in equation number 1. So that formula we will first put here. Then the value of x1, it is given as 1 in the coordinate. Here you can see the x1 value is given as 1. So we have entered this part. So in this manner we need to put all the values of the n1 and the Cartesian coordinates for the 4 different nodes. So finally we are getting the equation number 7 and 8 in this manner. Next, if we simplify the equation number 7, then we are getting a relation in between the epsilon and x, which is x equals to 1/4 to 7 plus eta plus 2 epsilon, which is our equation number 9. Now if x is like this, then del x del epsilon, this is 1/4 into 0 plus 2. So this is the first order differentiation we have performed here with respect to epsilon, and that means del x del epsilon, this is equals to half. Now, so again we can calculate del x del eta, this is equals to 1/4, which we are getting as equation number 11. Now simplifying the equation number 8, we are getting the relation in between y, eta and epsilon as equation number 12. Now if we perform this del y del epsilon, then we are getting the value as 0.125 multiplied by 1 plus eta. Again, if we perform the value or the differentiation of y with respect to eta, then we are getting that del y del eta, this is 0.125 into 5 plus epsilon. This is our equation number 14. Now to calculate the Jacobian matrix, we need to write the matrix here first. The Jacobian matrix equals to a 2 by 2 matrix of J11, J12, J21 and J22. Here the value of J11, it is del x del epsilon. Then J12, this is del y del epsilon. And J21, it is del x del eta, and J22, it is del y del eta. All the values of this J matrix we have already calculated. So if we need to only enter this value of this J matrix, and finally we are getting the Jacobian matrix as a 2 by 2 matrix as half, then 0.125 into 1 plus eta, then 1/4 and 0.125 and 5 plus epsilon. So these are the 3 different numericals that we have discussed in this lecture, where we have calculated the Jacobian matrix, then the element stiffness matrix, then the stress strain relationship matrix, all these things where we have used the formula for the Jacobian matrix, then the formula of the shape functions, all these different formulas which are actually very complex. So a lot of practice is required to solve such numericals based on the quadrilateral element for this isoparametric element. So this is the end for this lecture, and in the next lecture we will discuss the serendipity elements and Gaussian quadrature.